Hi, this is a video I hope will help everybody in my rocketry class uh, understand how to do problem number 4. This one is, if you know how to do this, you know how to do a lot of problems. And this is really much more straightforward than you think, so let's take a look at this. Here's the problem. The Saturn IV, which took us from Florida to the moon, weighs 6.3 million pounds. What is its acceleration if the thrust of each of the 5 boosters was 1.5 million pounds of thrust? And then they give us a hint. You must first convert the weight to mass. Okay, so I'm going to start on here. We're going to first convert our weight to mass. Now, if you look in your notes, you'll notice that there was some notes early in the semester where we said that weight is equal to mass times g. So mass times g. Okay. So if weight equals mass times g, then what we need to do is figure out the mass. And our weight, we said it's 6.3 million pounds. I'm going to say 6.3 million MLB, Major League Baseball, million pounds, is equal to mass, I don't know what that is, times gravity, which is 32 feet per second squared. And I just knew that number. You'd be allowed to look that up. That's not a problem. So 6.3 million pounds. How do I get this mass all by itself? Well, it's this 32 over here that's messing things up. So if I divide by 32 here, and I divide by 32 here, what I'm going to get, and I'm going to need to pull up a calculator for this. So I know you can't see this, so it's like you're going, what the heck? 6.3 divided by 32 equals 0.19 million pounds. But it's actually not really pounds, is it? It's actually, we're using a unit called, the unit is actually called a slug. And 0.19 million slugs, I'll say SL. That's actually the unit of mass in the English system of units. Now I'm going to put this off to the side. 0.19 million slugs. And now I'm going to do is erase all this other stuff so that I've got some room to finish the problem here. I say that's the first step, but it's really not all of it. We've got to twix us. Was its acceleration if the thrust of the 5? Now let's draw a picture. Now I'm not going to draw a picture of a rocket. I'm just going to say here, that dot is the rocket. And we've got thrust pushing up this way, and pulling down is weight. The thrust we know is going to be bigger than the weight. And so that will give us a net force. If I add up all the forces together, this is just a picture from the clock. Let me make a better sigma. The clock has the picture where if I add up all the forces, that's going to equal a mass times acceleration. Well, I've got the force of the thrust. It's going up. I'll say that's the positive direction. Now, how much is the force of that thrust? Well, it says it's 1.5 million pounds of thrust, but there's 5 boosters which do that. So if I say 1.5 million times 5, now is that the only force there? No, we've got the weight that's pulling down, so we minus that. And now this is 6.3 million pounds. is going to equal to mass times acceleration. I'll come back to that in a second. 1.5 times 5, well, 1.5 times 5 times 2 is 3, times 4 is 6, times 5 has to be 7.5 million pounds of thrust, minus 6.3 million pounds of weight. Get back to those again. 7.5 minus 6.3 is 1.2 million pounds equals, and now I'm going to 0.19 megaslugs times our acceleration. So 1.2, now I want that acceleration now, and I'm just going to divide both sides by 0.19. 1.2 divided by 1.9 is going to equal, it's all going to equal my acceleration over here. Yeah, it went away. It doesn't, doing this in Microsoft Word, it doesn't like it when I write slowly. Okay, that didn't go away. So 1.2 divided by 1.9, you'll probably hear some clicking of the calculator again. Not 1.9, it's 0.19. I'll fix that when I type it in. 0.2 divided by 0.19 gives me 6.31. That's not that, yeah, that's not that much. 6.31 feet per second squared. So the initial acceleration of this rocket that actually took us to the moon wasn't that much. We'll talk more about what happens while a rocket is in flight. I'm going to erase this now. So more about what happens with a rocket in flight. But one of the things you can think about is, did this thing, when we did this, does the mass of the rocket stay the same all the way up? Well, it starts at 6.31 feet per second squared, but we're using fuel to do that. So actually the mass of the rocket will go down. We're going to find out ways to make that a simpler problem without trying to break our heads with that really complex idea. But it's still something to remember. The mass of the rocket is going to go down, which means that this acceleration is going to go up. Okay, so I hope that helps with the rest of the assignment. We'll be talking more about it in class today, but I will set this up so you don't have to turn it in until tomorrow in case you have troubles with it still. Take care, and may all your problems have solutions.